The Atlantic was dying, not from storm or tide, but from steel-hulled predators that moved unseen beneath the waves. By late 1941, the U-boat menace had reached a crescendo, threatening the lifelines of the Allied world. Merchant convoys vanished in the night, leaving only a string of survivors and burning wreckage behind. From the icy waters off Newfoundland to the shipping lanes off Cape Hatteras, German submarines prowled with ruthless efficiency, picking off tankers, freighters, and cargo vessels with impunity. On average, 8 ships were being lost each day to torpedoes, mines, and gunfire. Supplies of food, ammunition, and industrial raw materials, a continent's lifeblood, were hemorrhaging into the sea. Across the US, the urgency of the crisis could not be overstated. War production had begun to accelerate, but American shipyards were shackled by tradition. Building a cargo ship was a measured, painstaking process. Laying the keel, riveting steel plates, carefully fitting the engine, and finally launching the vessel. A Liberty ship, a design intended for speed of construction, simplicity, and utility, still required, on average, 230 days from the first bolt of steel to its inaugural voyage. At that pace, the shipping losses would outstrip the ability to replace them, and the fragile lifeline to Britain and beyond would collapse. In Washington, the U.S. Maritime Commission convened in tense, smoke-filled rooms. The commission, tasked with overseeing the construction of merchant vessels, was staffed with bureaucrats, naval engineers, and logistics specialists. They debated endlessly over designs, schedules, and the feasibility of faster production, but the numbers were stubborn. Traditional shipbuilding had limits. The human and mechanical processes were thought to be immutable. The bureaucrats' solution, as always, was incremental improvement. A day here, a week there. But a day lost in wartime Atlantic waters was more than a day. It could be a convoy, a port, or 1,000 tons of essential supplies. Meanwhile, in the industrial heart of America, one man was watching the situation with a mix of disbelief and fascination. Henry J. Kaiser was not a naval officer, nor a shipwright, nor a government official. He was a civilian industrialist, a man who had cut his teeth on construction projects that stretched across the country: dams, roads, bridges, even monumental housing projects. He understood efficiency, scale, and human labor in a way that the Washington bureaucrats could not. And in 1941, as U-boat sinkings reached a perilous rate along the U.S. East Coast, Kaiser had a thought that would seem, to most, utterly insane. What if, he asked quietly to his inner circle, we didn't build ships like we always have? What if we built them like cars? The idea sounded ridiculous on paper. Ships were enormous, delicate, and complex. They required thousands of workers, months of painstaking effort, and a careful adherence to naval specifications. To liken them to automobiles seemed almost sacrilegious. But to Kaiser, this was simply an engineering problem waiting for a logistical solution. He envisioned a shipyard where prefabricated sections were assembled in parallel, where welding could replace labor-intensive riveting, where industrial scale and assembly line methodology could shrink construction timelines from 230 days to a fraction of that. In the offices of the U.S. Maritime Commission, his proposal was met with skepticism bordering on derision. Senior naval engineers shook their heads. "A cargo ship in under a month," one muttered, his voice thick with disbelief. "Impossible. You can't rush steel, sir. You can't force perfection." The bureaucrats insisted that traditional methods ensured seaworthiness and safety. They feared that rushing a vessel would make it a death trap, an unseaworthy hulk floating to the bottom of the Atlantic. Kaiser, however, saw the human cost differently. The hundreds of thousands of sailors and merchant mariners lost to U-boats because there simply weren't enough ships to carry essential supplies. On the docks themselves, a different story was unfolding. Thousands of men, and increasingly women, drawn into the workforce by necessity, labored with a mix of exhaustion and pride. Dock workers, riveters, and welders went about their routines in the colossal shipyards of the East Coast, New Jersey, and the Pacific Northwest. Their work was skilled, repetitive, and grueling. Every bolt and steel plate mattered. Mistakes could be fatal at sea. But the pace was slow, methodical, and insufficient to meet the mounting demand. Kaiser walked among them, not as a distant executive, but as an observer of process, a man searching for inefficiencies that could be pruned without sacrificing safety. The Atlantic's blood toll was rising. Convoys returning from Britain carried ghostly reminders of the cost of delay: lifeboats, shattered hulls, charred cargo holds. Each lost Liberty ship represented hundreds of tons of supplies gone, weeks of production wasted, and lives endangered. In the midst of this crisis, the question was stark and simple. How do you build a ship faster than the U-boats can sink it? Kaiser's answer, which he began proposing quietly to Navy liaisons and shipyard managers, was radical. Prefabrication, assembly line construction, welding over riveting, overlapping schedules, multiple ships under simultaneous construction in different stages. To the trained naval eye, it was almost heretical, but Kaiser had faith in the industrial process, and he had an army of engineers ready to execute. And so, as the first frost of 1942 crept along the Atlantic coast and the black funnels of U-boats pierced the horizon, a question lingered in the halls of the Navy and in the minds of the Maritime Commission. Could one civilian, with no naval background, really build a cargo ship in under a month? Could human ingenuity, industrial audacity, and sheer willpower bend the laws of shipbuilding and alter the course of a global war? The Atlantic, for now, waited. Its waters churned with the unseen menace of German submarines, indifferent to politics, bureaucracy, or ambition. Somewhere in the fog, convoys sailed, their fate tethered to the ships that would soon rise from the assembly lines of a man who refused to accept the impossible. The race against the U-boats had begun, and the first challenge was clear: prove that a Liberty ship could be built not in 230 days, but in mere weeks before the ocean claimed more victims than America could replace. In January 1942, the U.S. Maritime Commission's offices were quiet, save for the low murmur of clerks shuffling papers and the occasional ring of a telephone. Outside, the Atlantic churned with menace, wolf packs prowled the shipping lanes, and reports of sunk vessels arrived daily by wire. The situation was desperate. Yet Washington moved at the glacial pace of bureaucracy, reviewing reports, debating specifications, and issuing incremental recommendations. It was the sort of environment where radical ideas went to die. Into this world walked Henry J. Kaiser, carrying nothing but confidence, a notebook of sketches, and a vision that would have seemed reckless to the most daring of naval officers. He had spent weeks traveling between shipyards, observing processes, taking meticulous notes, and talking to engineers, foremen, and dock workers. Everywhere he went, the message was the same: shipbuilding was slow, expensive, and resistant to change. The Maritime Commission had insisted that a Liberty ship could not be built faster than 230 days, an immutable law. Kaiser did not see a law. He saw a problem, and to him, problems had solutions. The plan he presented to the Commission was so audacious that some officers later described it as bordering on madness. Kaiser proposed a system that seemed almost unimaginable, breaking the ship down into prefabricated sections that could be built simultaneously in separate locations, then transported to the slipway for rapid assembly. He advocated replacing traditional riveting with welding, a method still considered novel for large ships, arguing that it was faster, required fewer laborers, and, if executed correctly, was just as strong. He suggested overlapping schedules. While one section of the ship was being welded, another could be outfitted with machinery, another painted, and another inspected, all moving in a carefully orchestrated rhythm. To the naval engineers, the idea was alarming. Welding, they argued, could create brittle joints if not done properly. Prefabrication might introduce misalignments. Overlapping schedules could lead to confusion, mistakes, and dangerous shortcuts. "We are talking about vessels that must cross the Atlantic," one senior engineer told Kaiser. "These are not automobiles. A single flaw could sink a ship and everyone aboard." Kaiser listened, nodded, and smiled. "Gentlemen, the flaw is in the method, not in the material. With proper planning, oversight, and training, this can be done safely. The alternative is losing supply ships faster than we can build them, and that is not an option." The boldness of his proposal lay not only in the technical aspects but in the audacity of scale. Kaiser envisioned not one ship being built faster, but dozens, rolling off multiple slipways every month, a continuous production line capable of replacing lost tonnage before it could disappear beneath the waves. To achieve this, he required enormous coordination. Thousands of workers trained in welding instead of riveting, engineers to design prefabricated sections with precise tolerances, suppliers to deliver steel, engines, and components just in time, and a management structure capable of synchronizing hundreds of moving parts simultaneously. Many doubted it could be done. One Maritime Commission official later recalled the first presentation. "We thought he was joking. It sounded like science fiction. A ship in under a month? We couldn't even imagine a slipway turning out a vessel in less than half a year." But Kaiser had proof from other industries. He had built large-scale dams and housing projects with methods that, while unconventional, had proven remarkably efficient. He understood workflow, bottlenecks, and industrial psychology. More importantly, he understood that human labor could be leveraged, organized, and motivated to achieve extraordinary results. His philosophy was simple. If a process could be broken down into repeatable parallel tasks, it could be executed faster without sacrificing quality. To demonstrate feasibility, Kaiser called upon engineers to create mock-ups of prefabricated sections. They built small-scale models, practicing welding, assembly, and alignment. The first tests were clumsy riveters resisted welding, steel plates warped under inexperienced hands, and schedules collided. Yet, each failure was analyzed, refined, and corrected. Kaiser insisted on continuous improvement, a methodical approach that combined trial and error with careful documentation. Meanwhile, the Navy and Maritime Commission were under immense pressure. Reports of lost convoys arrived daily. Tankers torpedoed off Cape Cod, cargo ships disappearing near Bermuda, and freighters vanishing along the Carolina coast. Each loss tightened the vice around Allied logistics, pushing Washington closer to desperation. The public, unaware of the full scale of the crisis, read vague newspaper headlines, "Atlantic shipping losses mount." The sense of urgency, however, was palpable in every office where officials faced charts of lost tonnage and rising demands. Kaiser's proposal arrived at the perfect time. The Maritime Commission, though skeptical, recognized the stakes. A meeting was convened, bringing together engineers, shipyard managers, and Navy liaisons. Kaiser laid out his plan in painstaking detail, drawing diagrams, timelines, and resource charts. He emphasized speed without compromise, efficiency without chaos. His argument was compelling. If even half of his vision could be realized, the United States could replace ships faster than the U-boats could sink them, securing vital supply lines across the Atlantic. There was still hesitation. "Even if you can build one ship in 30 days, what about the workforce? The steel? The docks?" asked one naval officer. Kaiser leaned forward, eyes bright. "We will train the workforce. We will source the steel. And we will expand the docks. We are not asking for miracles. We are asking for organization, planning, and courage to try something new." The term insane was whispered more than once, but history shows that often innovation is mistaken for madness until it succeeds. Kaiser was no longer just an industrialist. He was a force of urgency, a civilian challenging centuries of naval tradition at the very moment the Atlantic demanded it. By the end of the meeting, a tentative agreement was reached. Kaiser would be allowed to prove the method in a pilot shipyard, under close supervision, with engineers documenting every step. On the docks, the word of the experiment spread quickly. Workers were intrigued, skeptical, but also motivated. Here was a chance to be part of something unprecedented. Building a ship faster than anyone had thought possible. The race was no longer theoretical. It had begun, and every bolt, every weld, and every plank mattered more than ever before. As the first prefabricated sections were rolled out onto the slipway, the Atlantic waited, indifferent and relentless. Somewhere beyond the horizon, U-boats continued their silent patrols, unaware that a single civilian's bold vision might soon turn the tide. The stage was set, the challenge defined, and the question hung in the air like a spectre. Could one man, one idea, and a determined workforce rewrite the rules of shipbuilding and save the lifeline to Europe before the ocean claimed more victims than could be replaced? February 1942. Richmond, California shipyard hazone of the Kaiser Corporation hummed like a mechanical heartbeat. Smokestacks emitted steady plumes as steel plates were cut, shaped, and lined up with precision. It was a cold morning, and the fog rolling in from the San Francisco Bay gave the docks a ghostly, almost surreal quality. For the men and women assembled here, however, this was no time for romance. It was a trial by fire. The experiment was simple in concept but daunting in execution. Build a Liberty ship in record time, using prefabricated sections welded together, with overlapping workflows designed to shave months off traditional schedules. In practice, it was chaos controlled by genius. Steel plates had to be cut to exact tolerances. Riveters, trained for decades in traditional shipbuilding methods, now found themselves being instructed to weld seams that would carry the weight of engines, cargo, and the ocean itself. Mistakes could be catastrophic. Captain Thomas K. White, a liaison from the Navy assigned to observe the project, walked the yard with a clipboard in hand, taking notes on weld quality, material handling, and worker safety. "I've seen shipyards before," he remarked to his aide, "but nothing like this. It's like trying to assemble an airplane on a battleship schedule." His words carried both awe and skepticism. The first prefabricated section, a bow frame 80 feet long, was hoisted into place. Workers held their breaths as welders began fusing the steel plates together. Sparks flew like miniature fireworks, and the air was filled with the acrid smell of molten metal. A veteran riveter named Samuel Ortiz, who had spent 30 years joining hulls by hand, muttered to no one in particular, "This'll never hold." Kaiser, observing from the supervisor's platform, simply nodded. He had anticipated doubts, and he had anticipated mistakes. Indeed, the first errors were immediate. Plates warped under the intense heat of the welding torches. Some welds were uneven, causing gaps that would require grinding and patching. Mistakes that would have been minor in a traditional 230-day schedule now loomed large, threatening to derail the entire experiment. Kaiser called a halt. He gathered the lead engineers and welders around a makeshift table cluttered with blueprints, notebooks, and coffee-stained diagrams. "We expected this," Kaiser said plainly. "Perfection on the first try is a fantasy. But what we cannot afford is complacency. Each flaw tells us where the process must adapt. That's how we learn faster than tradition ever will." What followed was a whirlwind of retraining. Workers who had spent decades perfecting rivets learned to control welding torches, practicing heat control, seam alignment, and rapid inspection. Engineers developed jigs and clamps to hold prefabricated sections in precise alignment, ensuring that once hoisted, pieces would fit together like clockwork. The shipyard itself was reorganized into specialized stations, each responsible for one aspect of assembly bow frames, midship blocks, stern sections, engine mounts. Supplies were delivered in exact order, timed to the minute, so that no worker was idle while waiting for steel or components. By late February, progress was visible. Sections that once took weeks to rivet were now welded in days. Labor that would have been sequential, one team finishing before another began, was now parallelized. The yard thrummed with energy as forklifts transported sections into place, cranes swung massive hull pieces into alignment, and welders followed precise schedules, synchronized like dancers in a performance of industrial choreography. Despite these gains, tensions ran high. Navy inspectors, conditioned to methodical, cautious shipbuilding, scrutinized every weld and alignment. Each inspection was an opportunity for criticism, and Kaiser welcomed it. "If you see a flaw," he told the inspectors, "point it out immediately. The only way this works is if we trust feedback more than ego." Some observers still whispered about the insanity of building a ship in weeks instead of months, but the sight of the hull slowly taking shape silenced most skeptics. On March 1, the first major milestone arrived. The keel, the backbone of the Liberty ship, was set in place, welded with precision, and held steady by temporary supports. Workers cheered, though quietly superstitions ran deep in shipyards, and it was considered bad luck to celebrate before the vessel touched water. Yet the sense of achievement was palpable. Here, under fog and steel, a vision was becoming reality. Kaiser's true genius lay not only in the methodology, but in the human element. He insisted that morale be high, providing hot meals, proper safety gear, and recognition for exceptional work. Letters from home were posted in the yard, workers were rotated to avoid fatigue, and supervisors held daily briefings to address challenges. In every corner of the shipyard, it was clear. This was more than construction, it was a collaboration between innovation and sheer determination. By mid-March, the first full prefabricated hull sections had been joined. The ship no longer existed as a collection of plates but as a coherent, floating framework, recognizable as a Liberty ship. Navy inspectors walked the decks, measuring weld penetration, checking tolerances, and testing integrity. Even the harshest critics nodded in approval. The ship would float, and it would carry cargo across the Atlantic. Kaiser, however, was not content. He turned his attention to optimizing further. Cranes were repositioned to reduce lifting time, welding teams were staggered to allow continuous operation day and night, and steel deliveries were scheduled to arrive just as a section was ready. Every delay, every minor bottleneck, was identified and eliminated. The experiment had grown beyond a single ship. It was becoming a system, a production model that could be scaled across multiple yards. By the end of March, the yard was a different place. Where chaos had once reigned, precision now governed every movement. Prefabricated sections, welded and tested, waited to be joined. Workers moved with purpose, and the ship itself loomed large, a testament to innovation, risk, and the unyielding will of a civilian who refused to accept the impossible. In Washington, reports of progress reached anxious ears. Officials who had doubted the feasibility of Kaiser's plan began to whisper a new word: hope. The Atlantic may still have been dying. But here, in the fog of Richmond, a blueprint for salvation was emerging, one welded seam at a time. The real test was yet to come. Could this experimental ship be completed, outfitted, and launched in record time? Could the methods hold under the pressures of scale, human error, and wartime urgency? The Atlantic waited, merciless and patient, as a single shipyard prepared to challenge the conventions of shipbuilding and, perhaps, rewrite the rules of war logistics entirely. April 1942. Richmond's Kaiser shipyard Hashone was alive with a mechanical symphony. Cranes creaked and swung massive steel sections, while welders' torches spat sparks in a choreographed rhythm. In just 6 weeks, the first experimental Liberty ship, dubbed SS Patrick Henry, had progressed from bare keel to near-complete hull. The shipyard's workers, engineers, welders, riggers, and labourers had begun to understand that what had once seemed impossible was now a matter of procedure. Henry J. Kaiser, surveying the yard from his elevated office overlooking the waterfront, noted the efficiency with a mixture of pride and urgency. "Every delay we remove," he told his aides, "every bottleneck we solve, means supplies reach the Atlantic faster, and that means fewer convoys lost to U-boats." The stakes were enormous. In the first 4 months of 1942 alone, German wolf packs had sunk more than 300 Allied ships off the U.S. East Coast, leaving convoys dangerously stretched and ports struggling to handle the backlog. The keystone of Kaiser's innovation was prefabrication. Instead of building ships sequentially, in painstaking layers, the yard now operated in parallel. Bow, midship, and stern sections were constructed simultaneously, often in entirely separate facilities, then moved via rail tracks and cranes to the slipway for assembly. Welding, once regarded with suspicion in heavy ship construction, became the primary method of joining steel. It was faster, required fewer skilled riveters, and allowed sections to be joined with unprecedented speed. On April 7, a record-breaking milestone was reached. The hull of Patrick Henry was fully assembled in just 41 days from keel laying. Naval inspectors, initially skeptical, were astonished at the structural integrity of the welded sections. Some older shipbuilders muttered about the risks of welding over riveting, citing fears of brittle fracture or hull failure, but repeated load and stress tests proved the ship seaworthy. The success emboldened Kaiser to push further, aiming for a complete outfitting engines, superstructure, and fittings in a fraction of the previous 230-day schedule. The human element was as critical as the technology. Women, recruited en masse as welders and fitters, took positions that had traditionally been reserved for men, their precision and endurance contributing directly to the accelerated schedule. Labor unions, initially wary, negotiated agreements that allowed round-the-clock shifts while ensuring safety and fair pay. Engineers rotated rapidly, sharing insights and troubleshooting errors immediately, a system that prevented delays from compounding. The result was a synchronized dance of metal and manpower, faster than any traditional shipyard could achieve. On April 10, Kaiser introduced a radical procedural innovation, the moving assembly line for hull sections. Rather than waiting for a section to be fully completed before transporting it to the slipway, partially welded sections were moved incrementally, allowing overlapping work by multiple teams. Bow and stern sections were advanced along rails, while midship blocks were welded in place, and simultaneously, engines were installed in modular units pre-assembled elsewhere. By minimizing idle time, every shift, day or night, was made productive. Meanwhile, the Navy closely monitored the experiments. Captain Thomas K. White, the liaison who had observed the initial trials, recorded detailed notes on workflow efficiency, weld quality, and safety protocols. "It's almost inconceivable," he wrote, "that a ship of this size, carrying thousands of tons of cargo, could be assembled in under 50 days without structural compromise. Yet the evidence is clear. It is happening." April 12 marked the day of the Patrick Henry's launch. Cranes lifted the final sections into place, welders made last-minute adjustments, and the ship was carefully lowered into the water. Dockworkers held their breath as the vessel glided into the San Francisco Bay. To everyone's amazement, it floated perfectly, free of leaks, perfectly balanced. Patrick Henry had become the first Liberty ship to be built in a single, continuous process that was faster than any previous record. The success had immediate strategic implications. At a time when U-boat attacks threatened to choke off supplies in the Atlantic, a ship built in weeks rather than months represented a paradigm shift. The Navy realized that convoy schedules could now be supported by a near-constant flow of cargo vessels, reducing losses and improving Allied resilience. Logistics planners in Washington began to consider how this production method could be scaled to multiple shipyards along both coasts. Kaiser, however, refused to rest. Within days, his team had already analyzed the workflow, identifying areas where further gains could be achieved. Prefabricated sections were standardized to the inch, cranes were rerouted to minimize movement, and welding teams were staggered to allow near-continuous operation. The goal was audacious: build a Liberty ship in under 30 days. By late April, the yard had moved from experimentation to mass production. Every new ship incorporated lessons learned from Patrick Henry, and output began to accelerate. The Atlantic may have been under siege, but in Richmond, innovation was proving that industrial ingenuity could outpace the threat. One civilian's vision, the insane idea of building a ship in weeks instead of months, was transforming into a tangible operational reality. For the men and women on the docks, the sense of purpose was electrifying. They were no longer simply constructing steel vessels. They were building hope for the war effort, one weld at a time. And as the next hull began to rise, faster and more efficiently than the first, it became clear that the era of slow, traditional shipbuilding was over. A new age had begun, an age in which Liberty ships could roll out every 4 days, ready to confront the Atlantic and supply the Allied cause. By May 1942, the success at Richmond was no longer an isolated marvel. It was a blueprint for national mobilization. Henry J. Kaiser's experimental techniques had proven that Liberty ships could be assembled in record time, and the U.S. Maritime Commission realized the strategic potential. If one yard could do it, multiple yards could do it. The challenge now was scaling the process to a level that could meet the Allied logistical demands in the Atlantic and Pacific theaters. Kaiser, ever pragmatic, began a series of visits to other shipyards along the East Coast, including the sprawling facilities at Portland, Oregon, and Richmond's sister yards in California. Engineers from each site were trained in the prefabrication and moving assembly line methods pioneered at Richmond. Standardized steel sections were now shipped across the country by rail, allowing yards to maintain a continuous supply of modules. Each yard adopted the same modular designs, with identical measurements, weld patterns, and quality controls. What had once been a craft-based operation was now an industrial symphony of repetition and precision. Meanwhile, labor recruitment expanded dramatically. Women, previously discouraged from heavy industrial work, were now actively encouraged to join the shipbuilding workforce. The Rosie the Riveter campaign gained traction alongside the Liberty Ship program, emphasizing both patriotism and necessity. African American workers, too, were increasingly employed in roles that had been traditionally segregated or restricted. By mid-1942, Kaiser shipyards were operating around the clock, with 3 shifts cycling in 24-hour intervals. Efficiency metrics were tracked daily. If a bottleneck appeared in one yard, the solution was quickly replicated across the network. The results were staggering. Where a traditional cargo ship had required 230 days from keel to launch, prefabricated Liberty ships could now be completed in under 60 days routinely. But innovation did not stop there. Inspired by a combination of industrial foresight and relentless management, the Richmond yard began experimenting with overlapping construction cycles. While one ship's hull was being completed, the next vessel's sections were already being fabricated in parallel. This approach effectively reduced average production time for subsequent vessels, setting the stage for the historic 27-day SS Joseph N. Teal build in November 1942, a milestone that would shock naval planners and industry experts alike. Washington, D.C., took notice. The War Production Board began coordinating steel allocation, welding equipment, and workforce training to support the expansion of Kaiser-style production nationwide. Congressional oversight committees visited the yards, marveling at the sheer scale of operations and the audacity of the civilian-led initiative. In official reports, the commission credited Kaiser and his engineers with saving months of supply chain time at a moment when the Atlantic convoy system teetered under U-boat pressure. The report cited that, without such rapid shipbuilding, supply lines to Britain, North Africa, and the Pacific could have been catastrophically delayed. Yet scaling the miracle was not without challenges. Early shipments of prefabricated sections revealed minor issues: misaligned steel plates, incomplete welding seams, and occasional shortages of engines or fittings. To overcome these obstacles, Kaiser implemented a rigorous quality control protocol that emphasized redundancy and verification. Inspectors were stationed at every stage, from the fabrication shops to the final slipway, ensuring that each modular section met structural standards before integration. Welding crews received continuous training, with errors analyzed and corrected in real time. This combination of procedural discipline and industrial innovation allowed production to accelerate without sacrificing the structural integrity or seaworthiness of the ships. The psychological impact on workers was profound. As ship after ship was launched faster than any previous records, morale soared. Steelworkers, welders, and dock laborers felt that they were directly contributing to the war effort on a scale previously unimaginable. Posters on the yard's walls proclaimed, "Every ship you build is a convoy saved," and workers internalized the message. It was more than employment, it was purpose, and in an era when morale could influence both productivity and the broader war effort, that sense of mission was invaluable. By late 1942, multiple Kaiser yards were operating in unison, delivering a new Liberty ship every 4 days, a pace that had seemed insane just months earlier. The Navy and Allied commanders could now plan convoys with unprecedented confidence, knowing that losses from U-boat attacks would not result in catastrophic shortages of supplies, ammunition, or vehicles. Liberty ships became the backbone of the Allied logistical network, linking continents and enabling sustained campaigns in North Africa, the Mediterranean, and the Pacific. Industry observers, both domestic and foreign, were stunned. A civilian industrialist with no formal naval background had transformed the principles of shipbuilding. What had once taken 7 to 8 months could now be done in mere weeks, and the methodology was being exported to shipyards along both coasts. Naval historians would later note that this civilian-led innovation was one of the decisive factors in maintaining the flow of Allied materiel at a critical juncture in the war. In the yards themselves, the revolution continued. Engineers experimented with pre-assembled engine modules, standardized deck fittings, and even semi-automated welding machines. Each iteration shaved hours from the production cycle. By the spring of 1943, the Liberty ship program had become a national industrial machine, coordinated, precise, and unstoppable. What had started as the bold suggestion of one civilian Kaiser himself had evolved into a nationwide system capable of sustaining the Allied war effort on both oceans. The Atlantic, which had once seemed to be dying under the onslaught of German U-boats, was now supplied at a pace that stunned even the most optimistic naval planners. Convoys no longer waited for months for new ships. Instead, they sailed confidently, their cargoes backed by a network of shipyards that had embraced innovation, human ingenuity, and sheer industrial audacity. Kaiser's insane idea had become reality. Liberty ships rolled out every 4 days, forever altering the course of the war. The heart of the Liberty ship revolution was not merely the workforce or the yards, it was the radical reimagining of shipbuilding itself. In pre-war America, ship construction followed centuries-old methods. Skilled craftsmen measured, cut, and welded each plate on site, often laboring for months on a single hull. The Kaiser team, however, embraced industrial principles borrowed from automobile manufacturing and adapted them to a scale that no one had imagined possible for ocean-going vessels. Prefabrication and the moving assembly line became the twin engines of the Liberty ship miracle. Prefabrication began with breaking the ship into hundreds of standardized sections. Each hull, once a monolithic structure, was dissected into modules: bow, midsection, stern, deck houses, and superstructures. These sections were fabricated simultaneously in specialized shops, often miles from the slipway where the final assembly would occur. Steel plates were cut to exact specifications, drilled with pre-marked holes for rivets and welds, and even partially fitted with machinery such as pumps, boilers, and engine mounts. By moving production off the slipway, yards eliminated the downtime caused by waiting for sequential construction tasks, a method that had historically been a bottleneck. The moving assembly line concept was applied to these prefabricated sections in a manner that resembled nothing so much as a floating puzzle. Cranes lifted enormous steel modules from storage areas onto the slipway, where they were aligned and welded in sequence. Teams specialized in specific tasks. Some focused exclusively on welding bulkheads, others on fitting decks, while machine crews installed engines and auxiliary systems. This division of labor allowed thousands of workers to operate simultaneously on different parts of a ship, rather than waiting for one hull to be completed before beginning another. The ingenuity of the assembly line lay in its timing and choreography. Sections arrived at the slipway according to a carefully calculated schedule. If one module was delayed, crews could shift to another task, ensuring that labor was never idle. Welding techniques, previously based on traditional hand fitting, were standardized across all yards. Workers followed blueprints with exact tolerances, and interchangeable parts meant that a section built in Oregon could fit perfectly on a hull in California. This level of precision, combined with relentless repetition, allowed for continuous acceleration of production. Yet, prefabrication was not without skepticism. Naval engineers initially feared that modular hulls might be structurally weaker than traditionally built ships. To counter this, Kaiser and his chief engineers implemented rigorous testing. Sample sections underwent stress tests, simulated sea conditions, and repeated inspections for weld integrity. The results proved that prefabricated Liberty ships were not only seaworthy, but remarkably resilient. Ships built in record time could withstand the pounding of the North Atlantic, survive torpedo strikes in some cases, and deliver their cargo reliably to ports under enemy threat. Technological innovation complemented human labor. Specialized cranes capable of lifting hundreds of tons of steel sections were introduced, and conveyor systems moved smaller components to precise locations on the hull. Welding machines were upgraded to deliver consistent heat, reducing the risk of weak seams. Electric arc welding replaced many traditional riveting tasks, cutting both labor hours and the physical strain on workers. Where a Liberty ship might have required 225,000 man-hours in traditional construction, prefabrication, and assembly line techniques reduced the figure dramatically, often by more than 50%. The human element remained critical. Supervisors organized crews into disciplined units, rotating teams between welding, fitting, and inspection to maintain both efficiency and morale. Training programs were instituted for new recruits, many of whom had never seen a ship before. By mid-1943, the Kaiser yards had become a massive classroom of industrial engineering, producing thousands of workers who could operate seamlessly in the high-pressure environment of rapid shipbuilding. Safety protocols, though rudimentary by modern standards, emphasized the prevention of accidents in a field where mistakes could delay an entire convoy schedule. One of the most audacious demonstrations of the system's potential occurred in November 1943. The SS Robert E. Peary was assembled in just 4 days and 15 hours, from keel laying to launch, setting a record that would never be broken. Observers from the Navy, the War Production Board, and Allied delegations flocked to the Richmond Yard to witness the feat. In press reports, the achievement was described as an industrial miracle, and workers, previously skeptical, now recognized that their labor was part of a historic transformation in war production. Prefabrication and the moving assembly line also had broader implications beyond Liberty ships. The methods developed by Kaiser were later applied to hospital construction, aircraft manufacturing, and even military base facilities. The war effort demanded rapid adaptation, and the success of modular construction in shipbuilding proved that industrial innovation could solve seemingly intractable problems. By the end of 1943, the Kaiser model had produced hundreds of Liberty ships, many of which were already crossing the Atlantic in convoys, carrying food, ammunition, and vehicles to the front lines. Enemy commanders, still unaware of the full scope of U.S. production capabilities, were surprised to see losses absorbed almost immediately. The modular approach allowed the Allies to replace ships faster than submarines could sink them, a strategic advantage that would prove decisive in the later years of the Battle of the Atlantic. The fusion of industrial engineering, innovative management, and sheer human determination had transformed the shipyards into an unstoppable engine of war. A civilian's insane idea had evolved into a structured methodology capable of producing ocean-going vessels at an unprecedented pace. Prefabrication and the moving assembly line were no longer experiments, they were the backbone of America's logistical triumph, ensuring that every convoy had the ships it needed, and that the Atlantic, once perilous and unpredictable, became a lifeline under Allied control. No engineering marvel, no matter how ingenious, could succeed without the people who powered it. The Liberty ship program, with its ambitious goal of cutting construction from 230 days to under a month, depended on an unprecedented mobilization of labor, skilled, semi-skilled, and untrained alike. At the Richmond Kaiser shipyards, the challenge was not merely to assemble ships but to orchestrate thousands of individuals, each performing specialized tasks with precise timing under conditions that were physically exhausting and mentally demanding. The labor pool drew from an extraordinary cross-section of American society. Men who had worked in factories, auto plants, and machine shops brought experience with tools and assembly lines, while an influx of women fueled by the Rosie the Riveter movement entered the shipyards in record numbers. Their contribution was transformative. By mid-1943, women made up nearly one-third of the workforce in some yards, taking on roles ranging from welding and riveting to electrical fitting and quality inspection. Many had never handled industrial machinery before, but intensive training programs and hands-on mentorship enabled rapid skill acquisition. Training was itself a logistical challenge. To build a Liberty ship in weeks, every worker needed to understand their role within the larger system. Kaiser's engineers devised modular instruction. Crews learned their tasks in isolation before integrating into the broader assembly sequence. Welding apprentices practiced on mock hull sections, while pipefitters assembled complex plumbing networks in dedicated workshops. This microcosm approach allowed new workers to gain competence quickly, reducing errors on the main slipways and ensuring consistent quality across all ships. Efficiency was not achieved solely through human effort, it required meticulous planning and logistical support. The Richmond Yard, sprawling across dozens of acres, functioned like a self-contained city. Steel arrived in pre-cut plates, often sourced from mills hundreds of miles away, timed to reach the slipway just as crews were ready to weld. Engines, boilers, and auxiliary machinery were shipped in modules, synchronized to avoid delays. Any misalignment in delivery schedules could halt progress, making the role of supply officers as critical as that of welders and riveters. Transportation logistics were equally complex. Trucks, rail lines, and conveyors moved raw materials to fabrication shops and then to the slipways with precision timing. Warehouse managers maintained inventories of every rivet, bolt, and electrical component, while engineers coordinated the movement of massive hull sections via overhead cranes. The synchronization of manpower, machinery, and materials mirrored the orchestration of a military operation, an apt metaphor, given that these ships would ultimately supply the front lines of a global conflict. Labor management also demanded innovation. Traditional hierarchical structures could not respond fast enough to the rapid pace of construction. Supervisors implemented decentralized decision-making, empowering foremen to resolve minor issues on the spot. Shift work was staggered to maintain a 24-hour production cycle, with crews rotating every 8 to 12 hours. Breaks were brief, but strategically timed to prevent fatigue while maintaining workflow. Safety, though not infallible, became a focus. Industrial accidents could disrupt the entire schedule, and morale suffered if workers felt endangered. Kaiser instituted basic safety protocols, supplemented with on-the-job oversight and peer accountability. Despite these measures, challenges abounded. Welding large sections of steel created intense heat, sparks, and noxious fumes. Workers labored outdoors in all weather conditions, summer heat, winter rain, and persistent fog from the nearby bay. Injuries were inevitable, yet the culture of collective purpose minimized downtime. Veterans recalled that the knowledge they were building ships faster than ever before, and knowing those ships were crucial to the war effort, drove them through the most grueling shifts. Union negotiations also shaped the labor environment. The shipyards navigated complex relationships with unions, balancing the need for speed with workers' rights and fair wages. Agreements were reached to allow overtime while preventing exploitative practices, and incentives such as performance bonuses motivated crews to surpass production targets. Productivity soared when workers saw tangible recognition for their contributions, reinforcing the human dimension of the industrial miracle. The human-machine interaction extended beyond laborers to the ships themselves. Every Liberty ship was, in essence, an assembly of micro-teams working in concert with cranes, conveyors, and lifting devices. Cranes were operated with precision to place 30-ton hull sections, while riveters and welders bonded the steel plates into a seaworthy structure. Even minor errors could propagate into costly rework, so inspectors monitored every stage, ensuring that human judgment complemented mechanical efficiency. The Liberty ship became a symphony of manpower and machinery, where timing, precision, and coordination were as critical as the quality of the materials. One remarkable aspect of this human-machine system was its adaptability. Crews quickly learned to respond to unforeseen delays, whether from late material deliveries, equipment malfunctions, or unexpected structural issues. Cross-training allowed workers to switch tasks fluidly, preventing bottlenecks. Foremen maintained detailed schedules and contingency plans, mirroring military logistics. By the end of 1943, the shipyards had reached a pace few thought possible. Ships that once took months to complete were rolling out every 2 weeks, and the rhythm of production seemed almost unstoppable. Ultimately, the Liberty ship program demonstrated that industrial scale and human ingenuity could converge to meet unprecedented wartime demands. Kaiser's civilian vision, once dismissed as impractical, had been realized through labor organization, logistical precision, and relentless dedication. Thousands of men and women, coordinated like a military battalion, had transformed a fragmented shipbuilding process into a seamless production machine. The Atlantic, once a theater of vulnerability, now had a constant stream of cargo ships, each a testament to the power of human coordination in the face of logistical complexity. By combining innovation with disciplined labor, the shipyards had not only produced vessels, they had created a blueprint for wartime industry that would echo for decades. The success of the Liberty ships proved that civilians, engineers, and ordinary workers could achieve what the Navy had once thought impossible, redefining the limits of production and turning industrial capacity into a decisive weapon of war. By late 1943, the Liberty ship program had transformed from an audacious idea into a benchmark of industrial achievement. What had begun as a civilian's insane proposition, building a cargo ship in under a month, was now producing vessels at an unprecedented rate. The Richmond shipyards were no longer merely construction sites. They were arenas of innovation, experimentation, and record-breaking performance. Each ship that slid into the water was both a logistical triumph and a psychological victory for a nation still reeling from losses in the Atlantic. The records were astonishing. In December 1943, the SS Robert E. Peary set a new milestone. From keel laying to launch in only 4 days, 15 hours, and 29 minutes. The feat stunned the maritime world. Newspapers called it miraculous, while naval officers, initially skeptical, began to reconsider their assumptions about civilian industrial capabilities. The achievement was not just a matter of speed. It represented a complete reimagining of production processes, where modular construction, prefabrication, and continuous workflow had converged into a single, unstoppable force. Prefabrication had become the cornerstone of the process. Engineers had divided ships into hundreds of standardized sections, each fabricated off the slipway in controlled workshops. Hull plates, deck segments, and superstructure modules were built in parallel, with workers specializing in a single type of assembly. When sections were ready, they were transported to the slipway, where cranes lifted them into position. The precision required was extraordinary. Alignment errors of even a few millimeters could compromise the integrity of the vessel. Yet, through meticulous planning and coordination, crews consistently achieved near-perfect fits. This new methodology broke decades of naval convention. Traditionally, ships had been built sequentially, layer by layer, with hulls constructed in place from keel to deck. Kaiser's approach challenged the orthodoxy by treating ships as enormous, three-dimensional puzzles. Prefabrication allowed for simultaneous construction of multiple sections, effectively compressing timelines by a factor of 10 or more. Engineers constantly refined the process, adjusting welding sequences, redesigning scaffolding, and experimenting with crane positioning to eliminate bottlenecks. Every innovation, no matter how minor, had a direct impact on production speed. The Navy and Maritime Commission, initially skeptical, became enthusiastic partners. Inspectors who had expected delays were impressed by the uniform quality and seaworthiness of the ships. They noted that the standardized construction actually improved durability, as uniform welding techniques and pre-measured components reduced structural inconsistencies. Common in traditional shipbuilding, in some respects, Liberty ships were stronger than their conventionally built predecessors, a testament to the precision that rapid modular construction could achieve. Public perception also shifted. Stories of 4-day ships captured headlines, inspiring both workers and civilians. Propaganda emphasized the heroic efforts of the labor force, portraying every welder, riveter, and crane operator as an essential participant in the war effort. Liberty ships became symbols of national ingenuity, tangible proof that America could mobilize its industrial base to meet the seemingly impossible. Even foreign observers, including Allied commanders, marveled at the speed and scale of production, noting that the US was reshaping the economics of maritime warfare. Despite the breakthroughs, challenges remained. Compressed timelines left little room for error, and occasional misalignments or welding defects required immediate remediation. Engineers instituted rigorous quality control, with inspectors stationed at every stage of assembly. Teams performed ultrasonic weld tests, visual inspections, and stress simulations to ensure that the vessels could withstand the rigors of transatlantic convoys. This emphasis on precision balanced speed with safety, preventing shortcuts from undermining the program's long-term effectiveness. Logistics, too, had to evolve. Supplying hundreds of prefabricated sections demanded unprecedented coordination with steel mills, rail networks, and component manufacturers. Delays in a single section could halt an entire slipway. To mitigate this, Kaiser's management implemented real-time tracking systems, allowing engineers to anticipate bottlenecks and adjust schedules dynamically. The integration of human oversight with logistical intelligence mirrored military operations, turning the shipyard into a microcosm of operational command and control. Perhaps the most remarkable aspect of this record-breaking pace was the culture it created. Workers became intensely competitive, striving to surpass previous production times without compromising quality. Incentive programs rewarded teams for completing sections ahead of schedule, and morale soared when new records were announced. Foremen reported that the shared sense of purpose, combined with visible, measurable progress, fostered extraordinary productivity. Labor disputes, which had initially threatened to slow construction, became rare as workers internalized pride in their collective achievement. The broader impact was profound. Every Liberty ship that entered service replenished depleted convoys, mitigated shipping losses, and strengthened Allied supply chains. By mid-1944, the United States was launching ships at a pace sufficient to offset losses to German U-boats, ensuring that troops, weapons, and supplies could reach Europe and the Pacific with unprecedented reliability. In this sense, the civilian innovation pioneered by Henry J. Kaiser was not merely a production miracle, it was a strategic weapon, a logistical lever that altered the course of the war. In retrospect, the success of the four-day ships can be attributed to the convergence of several factors: visionary leadership, modular engineering, disciplined labor, meticulous logistics, and relentless experimentation. Each element alone could have produced improvements, but only in combination did they achieve the seemingly impossible. The Liberty ships became living proof that the boundaries of industrial capability could be expanded through ingenuity, coordination, and a willingness to break with tradition. By the end of 1943, the shipyards had entered a rhythm that would define the remainder of the war. Every month, dozens of vessels launched from slipways across the United States, a testament to what civilian initiative could accomplish when coupled with engineering mastery and human determination. What had begun as an insane idea had become a cornerstone of Allied strategy, ensuring that the Atlantic would no longer be a graveyard of supply ships but a highway of victory, carrying the tools of war and the promise of triumph to distant theaters.